All right, we're going to try this again. You haven't been here for all the tries, so I should just not even tell you about them. All right, we are going over Physical Science, Module 14, Waves and Sound. Primarily, Dr. Weil is going to be focusing on sound in this chapter, but as an introduction to that, he is going to discuss the different kinds of waves in creation because sound is a wave. The transverse wave is probably the wave that we are most familiar with. We see it everywhere in creation, most notably when we go to the beach. Ocean waves are transverse waves. Notice that with the transverse wave that the disturbance that makes the wave is moving perpendicular to the direction that the wave is traveling. I think that's actually an easier way to remember it than Dr. Weil's definition in the book. In the book, he says a wave with a direction of propagation that is perpendicular to its direction of oscillation. And if we were together in class, I would be able to demonstrate that. I really don't want to use my phone or my time to demonstrate it here on this video. So I think what I'm going to do is just go ahead and have you look over this definition and try and see that definition when we take our quiz. So a transverse wave, once again, is a wave where the disturbance that makes the wave is moving perpendicular to the direction in which the wave is traveling. Now, if you have taken math, if you're in Algebra 1 this year, you should understand what perpendicular means. Notice that the vibration of the wave, the up and down arrow there, is moving perpendicular or at right angles to the way that the wave is traveling away from the lady in that particular diagram. Now with the transverse wave, the highest point of the wave we call the crest, and the lowest point of the wave we call the trough. We can measure the wavelength by measuring either from crest to crest or from trough to trough. We're going to use the Greek letter lambda to designate wavelength when we do our math later on in the chapter. In addition to the wavelength, we can also measure the amplitude of the wave. The amplitude of the wave is the height of the wave. And so I've drawn a line across the wave and cut the crests away from the troughs. And so the amplitude is the measure of how high a crest is or how low a trough is. So it's measuring the height of the crest or the depth of the trough. So we have the wavelength and the amplitude. The amplitude, when we do our math later on, is going to be designated with a capital letter A. In addition to the transverse wave, we also have the longitudinal wave. We're less familiar with longitudinal waves because in general in creation we can't see them. They are more waves that pass without being seen through air or through other things. If you want to see a longitudinal wave, you could make waves go through like a slinky or something. And if we were together in class, I usually do bring a slinky in. But since we're not together in class, I can't show you that today. So in the book, Dr. Weil says that a longitudinal wave is a wave with a direction of propagation that is parallel to its direction of oscillation. I think an easier way to remember that, and still this similar definition, is that in a longitudinal wave, the disturbance that makes up the wave is moving parallel to the direction in which the wave is traveling. That's much easier to understand and to remember. So notice that in the diagram there that the vibration of the wave is traveling in the same exact direction as the wave is traveling. And so they are parallel. They're on parallel paths. When you think of parallel, you think of train tracks going in the same direction. With a longitudinal wave, instead of having crests and troughs, we have compressions and rarefactions. The compressions are when the wave compresses itself into a smaller area. A rarefaction is where the wave expands, and you can see the difference in that diagram between the compressions and the rarefactions. Now, to help you remember what a rarefaction is, notice the word rare in there. If something is rare, you don't come across it very often. In fact, to be rarefied means to expand something so that it is a lot thinner and there's less over it in smaller surface areas, and it actually goes out over a larger surface area. When we were learning about the air in an earlier module, as you went higher and higher into the atmosphere, the air was more and more spread out, and scientifically would say that the air was more and more rarefied. So rarefactions are where the wave expands, compressions are where the wave compresses. Just like with the transverse wave, we can measure the wavelength of a longitudinal wave. Now here, instead of measuring from the center, from one crest to another crest or one trough to another trough, we're going to measure from the center of one compression to the center of the next compression, or the center of one rarefaction to the center of another rarefaction. And once again, we are going to use the Greek letter lambda to designate a wavelength when we do our math later on in the chapter. In addition to being able to measure the wavelength, we can measure the amplitude of a longitudinal wave, just like we did with a transverse wave. So it's hard to see there, but once again, I've drawn the line across the wave, and I've drawn a little arrow showing where you would measure the amplitude, but it's hard to see, so I'm going to go ahead and circle. That's where I have drawn the little arrow where we would measure the amplitude. So, and just like with the transverse wave, we're going to label the amplitude with a capital letter A when we do our math later on. Here is where I had hoped to be able to show you a video. The video didn't embed in my PowerPoint, so instead of showing the video right now, I think I'm going to just go ahead and give you a link to the video so that you can watch it. It's only 24 seconds long, but I think it'll be very helpful to show you the difference between a transverse wave and a longitudinal wave, since we can't be together in class and I can't show you in person. All right, remember that different waves have different wavelengths, different amplitudes, and different frequencies. So we've talked about the wavelength, we've talked about the amplitude, and now we're going to talk a little bit about the frequency. The frequency is how many times a wave hits a certain point every second. So when you think of ocean waves, if you count them as they come in, and you count how many times they hit you in a certain amount of time, that will tell you the frequency of those waves. We can mathematically figure out what the frequency is a wave by dividing the speed of the wave by the wavelength of the wave. And so we're going to use this equation right here, this formula, where F stands for the frequency of the wave, and that's what we're trying to find. V is going to stand for the speed of the wave, and the little Greek letter lambda is going to stand for the wavelength of the wave. So in order to find the frequency, we are going to divide the speed that the wave is traveling by its wavelength, and that will give us what the frequency is. That is how many times the wave hits a certain point every second. So once again, F equals V divided by lambda, or frequency equals speed divided by wavelength. Now we're going to put this into practice. What is the frequency of a wave that travels at a speed of 3 meters per second and has a wavelength of 0.5 meters? And so we're going to use our formula, and this is one that you need to memorize for the quiz. You need to memorize F equals V over lambda. Frequency equals speed divided by wavelength. Once you have that memorized, it's very easy and it's very simple just to plug the numbers into that equation. So I have frequency equals 3 meters per second divided by 0.5 meters. And the answer to that is 6. Very easy math. It's just a matter of memorizing the formula and knowing how to plug the information that you're given in the word problems into the formula. And we talked about needing to master that skill. So hopefully you have mastered it and can do this. So now we need to label it, and it's kind of got a strange label to it. We have meters divided by meters, so those are going to cancel out. I didn't cancel them out on my PowerPoint, but looking at it mathematically, remember that in science, we aren't just multiplying and dividing the numbers, we're also multiplying and dividing the stuff that goes with them. You know what I'm talking about, the stuff that goes with them, the meters, the seconds, the things like that. And so meters divided by meters is going to be, just like if you had 5 divided by 5, it's going to give you 1. It's nothing then. Meters divided by meters are going to equal 1 also. So they have canceled each other out, in other words. So we have 6 1 over seconds, which means nothing to me, but luckily for us, scientists have come up with a handy-dandy unit called the hertz. The hertz is a unit used to measure frequency and vibrations of waves. And so when we get to the end of frequency problems, rather than trying to figure out seconds, meters, and how do I label this, we can just go ahead and label it hertz, just a capital H and a lowercase z, hertz. So the answer is 6 hertz. We're going to do another one. What is the frequency of a wave that travels at a speed of 15 meters per second and has a wavelength of 0.3 meters? Once again, we're going to use our frequency equation. Frequency equals V divided by lambda, or speed divided by wavelength. And once again, we've been given the speed and we've been given the wavelength. So we just need to plug those numbers in. The frequency equals 15 divided by 0.3. And I may have done the math wrong there. I'll give you extra points if you can figure out that I got the math wrong done there. Looking at it right this second, 15 divided by 0.3 doesn't seem like it should be 5. It seems like it should be something else to me, maybe like 50. But earlier today, somehow that's what I got. Nevertheless, whether it's 5 or 50, we're going to label it hertz, and on we go. All right, from On Your Own question 14.1. I know you've already done this. I just want to go over it together so that it will help you go through the process again, and you learn how to use the equation again, the frequency equation. Remember that my new motto is that it's not so much knowing the answer as knowing how to get the answer. So here we go. A longitudinal wave is suddenly stretched so that its wavelength is increased. If the speed of the wave does not change, what will happen to the wave's frequency? So, just thinking of it logically, looking at the frequency equation, speed divided by wavelength. If the speed stays the same, but the wavelength is suddenly larger, you're dividing the speed by a larger number, and so the answer should be a smaller number. So going back to the one that I may or may not have gotten wrong, where frequency equaled 5 hertz, let's change the wavelength from 0.3 meters to 0.5 meters and see if we can get the answer. And so when you do the division, I have 3 hertz there. It's probably actually 30 hertz now that I'm re-looking at it. I must have been tired earlier today when I was working on this PowerPoint. So it should be 50 hertz and 30 hertz, but 30 hertz still is smaller than 50 hertz, so the frequency has decreased, even though I did my math a little bit wrong there. Sorry about that. And I gave myself a check mark saying I got it right, and now I'm realizing no, I didn't quite get it right. But I did, the frequency should decrease is the correct answer though. All right, next one. On your own, question 14.2. Suppose you are waiting on a beach that is experiencing waves that move with a speed of 0.5 meters per second and have a wavelength of 0.25 meters. If you stood still, how many waves would hit you every second? Once again, we're going to find the answer to this by using our frequency equation. Frequency equals speed divided by wavelength. I'm going to plug in the information we've been given, 0.5 meters per second divided by 0.25 meters, and we get a frequency of 2. Now this time, instead of labeling it hertz, we're not really looking for the frequency because that's not what the question asked. The question actually asked, if you stood still, how many times would the wave hit you every second? And the answer is every second it would hit me 2 times. That time I got the answer right. Yay! All right, so far we have talked about wavelength, we have talked about amplitude, we have talked about frequency, and now we're going to talk about speed. Remember that speed is the rate at which something is able to move. Now, I've asked you to memorize the frequency equation. Speed divided by wavelength. This equation, if we were going to get together in class, I probably would make you memorize it also, but because we're in such a weird time right now, I'm not going to make you memorize this one. When you get to the quiz, if we have questions like this on the quiz or on the test, I'm going to go ahead and give you this equation. But I think that it's worth going ahead and talking through this equation so that I'm sure that you understand it. In this equation, notice that we have V again, and last time V meant speed, and V is going to mean speed in this equation also. And the equation for speed is 331.5 plus 0.6 times T, which stands for the temperature in centigrade. And then we're going to label it meters per second, meters per second. Now, one other thing that I want to talk about here is the little dot there, and that means for you to multiply. Now, up to this point in your math career, you have learned to use the multiplication symbol, which is just a little x. And once you moved to algebra, you needed to put the x away, and we don't write multiplication symbols when we're doing algebra because we're working with numbers that can be variables, and often one of the variables that we use in algebra is the variable x, and so it becomes confusing if you're trying to multiply x by y and you have x, y. What does that mean? So you have learned there that you can also use parentheses to mean multiply. Well, in this particular equation, it would also be difficult to use parentheses to show the multiplication between the 0.6 and the temperature in centigrade. Centigrade is an alternate name for Celsius, by the way, and I'll probably go back and forth using both, centigrade, Celsius. So in this case, they've used a little dot there, and that's a little scientific way to say multiply these two numbers, multiply these two numbers. And you can see where in science that would be a better way to designate these two numbers need to be multiplied when you're using so many parentheses and so many complicated equations. Now, not in our class, we're not going to get that complicated in our class, but higher level science math, you do end up having very complicated equations with lots of parentheses, and so they've developed just that little shorthand, that little dot, and that also means to multiply. All right. Let's do some calculating of speed. If the temperature is 68 degrees Fahrenheit, which is 20 degrees Celsius or centigrade, what is the speed of sound? Now, the first thing I want to point out is that Dr. Weil there put in 68 degrees Fahrenheit, and you don't have to worry about that at all. That information is just put in there to confuse you. And so you're too smart for that. You're not going to be confused. You're going to look at that 20 degrees Celsius, and you're going to know that that's what we need to use when we do our calculation for speed. All right, there's our speed equation, which you're not going to have to memorize. Speed equals 331.5 plus 0.6 times the temperature in Celsius or centigrade, and the resulting label is going to be meters per second. So let's go ahead and put in the information that we know. We know that it's 20 degrees Celsius. So as we look at that, we also know, because of order of operations, that we need to do multiplication and division before we do addition and subtraction when we have complicated equations like this. So the first thing we're going to do is we're going to multiply 0.6 times 20 degrees. We get 12, and so then very easy, we are just going to add 12 to 331.5, and we will get the answer 343.5 meters per second. So we have calculated speed, and that's all that question asked us to do. We got it right, yay! Often we use calculations for speed of sound when we are trying to calculate how far away lightning is. Light moves faster than sound does, so we see the lightning long before we hear the sound of the thunder rolling by our ears. So, a more typical word problem for speed would be this one. A physicist is watching a thunderstorm. She sees a flash of lightning, and then hears a thunderclap 2 seconds later. If the air temperature is a cool 15 degrees Celsius, how far away from the physicist was the lightning formed? So we're going to go ahead and start with our speed equation. 331.5 plus 0.6 times the temperature in Celsius, and that will give us meters per second. The information that we have is that it is 15 degrees out. So we're going to go ahead and do the math. And once again, because of order of operations, we're going to multiply 0.6 times 15 degrees before we do the addition. We get 9. That's very easy to add to 331.5. And so we get a speed of 340.5 meters per second. But we're not done, because that's not what the question asked. It said, how far away from the physicist was the lightning? So this is going to be a two-step problem. And I'm sorry, I feel sorry for you, but it is a two-step problem. We got that right, by the way. We're going to go back to our speed equation that we learned several months ago in order to find what the distance is. Remember, I told you that if you would memorize the speed equation, that we could find out what the time traveled was, and we could find out what the distance traveled was just by algebraically manipulating the formula. And so I'm going to walk you through how to do that. First of all, I want you to remember that if you forget the speed equation, all you have to do is remember miles per hour. We drive all the time, and we talk about our distance in miles per hour. And when you remember miles per hour, then you're going to remember that speed is a distance divided by a time. So speed is the distance traveled divided by the time. All right, so next we need to go ahead and fill in the information that we have. We already know what the speed is. The speed we just figured out using our speed equation. The speed is 340.5 meters per second. We also know the time. It said that she heard the thunderclap 2 seconds later, so we can fill both of those in to the speed equation. 340.5 meters per second equals some distance, we don't know what the distance is, that's what we need to figure out, divided by 2 seconds. Now, if you are taking Algebra 1, this should not be very difficult for you to figure out. You know that whatever you do to one side of the equation, you can do to the other side of the equation. In order to isolate distance, we need to get rid of 2 seconds on that one side of the equation and stick it over on the other side of the equation so the distance is isolated and we know what the distance is. So the quickest, easiest way to do that is to multiply by the reciprocal. We need to multiply by the reciprocal. And I've kind of run out of space on this side, so I'm going to write it over here again. And so to multiply by the reciprocal, I'm going to notice that 2 is the denominator in the distance divided by seconds. So I'm going to flip it. I'm going to take the reciprocal, and I'm going to multiply distance divided by seconds. And in that case, seconds is in the numerator. I hope that makes sense to you. It should if you're taking Algebra 1 this year. Remember that with algebra, you always need to balance the equation. So whatever you do to one side of the equation, you have to do to the other side of the equation. So if I multiply by 2 seconds on the distance side of the equation so that I can cancel out seconds, then I also need to multiply the other side of the equation by 2 seconds. So I have gone ahead and I have canceled out my seconds on one side of the equation, isolating distance on that side of the equation. And then on the other side of the equation, I'm multiplying 2 seconds times 340.5 meters per second. And that will leave us with 600, when I do the multiplication, I end up with 681. And it's a distance, so we are left with meters. Actually, on that side of the equation, seconds also cancels out. But for some reason, I didn't put that in the PowerPoint, and so you just have to do that yourself, know that it happens, know that a distance measurement cannot be meters per second, so we're going to just have meters left, 681 meters. And we got the answer right. There's my check mark. Yay! All right, let's do it again. On your own, question 14.3, what is the speed of sound in air when the temperature is 28 degrees Celsius? Once again, we are going to use our speed equation, 331.5 plus 0.6 times the temperature in Celsius, and then we end up with meters per second. Putting in the information that we know, 28 degrees, we're going to multiply 0.6 times 28 first because of order of operations. We always multiply and divide before we add or subtract. We end up with 16.8. That's very easy to add to 331.5. And when we do, we get the answer 348.3 meters per second. That is the speed of sound in the air when it is 28 degrees Celsius out. And we got it right. Woohoo! I'm having fun with those check marks. All right, on your own, question 14.4. During a thunderstorm, the temperature is 18 degrees Celsius. If you see lightning flash and hear the thunder 1.5 seconds later, how far away did the lightning actually strike? So this is one of those that is 2 parts again. First, we need to find out what the speed of sound is when the temperature is 18 degrees Celsius. We're going to do that by using our speed equation, 331.5 plus 0.6 times the temperature in Celsius, and we'll get meters per second. We're going to add to the formula, just plug it in, 18 degrees Celsius. We're going to multiply 18 times 0.6 because of order of operations. We do multiplication first. We get 10.8. We're going to easily add that to 331.5, and we get a speed of 342.3 meters per second. That's pretty easy. All right, we got it right. Yay! Now we're going to figure out the distance, and we're going to figure out the distance by remembering miles per hour, and speed equals distance traveled divided by time traveled. We're going to plug in the information we know. We know that the speed is 342.3 meters per second. We know the time. We said that it's 1.5 seconds later. So we plug those both in, and then we're going to multiply both sides by the reciprocal of 1.5 seconds in the denominator. We're going to bring it up to the numerator, multiply both sides of the equation by that reciprocal, so that we can isolate distance on one side of the equation. Remember, with algebra, we need to, whatever we do to one side of the equation, we have to do to the other side of the equation. We have to keep it balanced. So we are going to multiply the distance side of the equation by 1.5 seconds so that we can cancel out 1.5 seconds and leave distance on that side of the equation all by itself. On the other side of the equation, we are multiplying 1.5 seconds times 342.3 meters per second. Once again, I didn't cancel out the seconds, but it does cancel out. Go ahead and do the multiplication, and you end up with, oops, I went too far, and you end up with a distance of 513.45 meters. 513.45 meters. So hopefully those make sense to you. If you're still having trouble with the math, you can always rewind this, sit down with a parent, have them go through it with you. And remember that while getting the correct answer is important, it is equally important to know how you get the right answer. If you just don't know how to get it, but you guess the right answer, you haven't learned anything, and you haven't gained anything. So it's important that you understand, and then, of course, have that green check mark there, get the right answer. That's always fun. All right. Remember that Dr. Wall said that the speed of sound is different in different substances. So sound travels differently through different substances. Remember that light travels the best through air, and that it slows down in water, and then it comes to a standstill in solids. Sound is the opposite. Sound travels a certain speed in air. It travels even faster in water. And then if it's going through something solid, it is able to travel even faster. And that should make sense to you because sound is a vibration. Sound is a vibration. And it's more difficult to vibrate gases than it is to vibrate liquids. And it's more difficult to vibrate liquids than it is to vibrate solids. And that's just because of how the atoms in those substances, in those phases of matter, are bunched together. In a gas, they're far apart. One atom might be vibrating, and then 2 feet away, another atom is vibrating. And so it's not as easy to pass on the vibration in air as it is in water, where the atoms are more closely packed and where it's easier to pass on the vibration, and even more so in solids. So the last part of the chapter today, well, actually not today, but this week, was a discussion about supersonic speed. So supersonic speed is any speed that is faster than the speed of sound in the substance of interest. And by the substance of interest, that means that through the substance that the thing going faster than sound is passing through. So, for example, if you were able to build a supersonic jet boat, it would be passing through water. And so if you go faster than the speed of sound in water, which would be very difficult to do, then you would be going supersonic speed. Much easier to go faster than the speed of sound through air. And that is actually what we're able to do at this point in history. I don't think that there is a supersonic speedboat. I just made that up. So remember that when something goes at or faster than the speed of sound, it causes what is called a sonic boom. And I actually have lived through a sonic boom. I grew up in Long Island, and at a time when the Concorde was still flying. It was a supersonic jet that took people from London to New York in about 3 hours, which is an incredibly fast speed. And so even though it was supposed to slow down as it was coming into New York, as it passed over Long Island, it still was going above the speed of sound, and we always had our windows rattle as the Concorde flew over us. So a sonic boom is the sound that is produced as a result of an object traveling at or above Mach 1. Remember that Mach 1 is the speed of sound. So I'll probably talk some more about Mach 1, Mach 2, Mach 3 next week. It's not going to be on your quiz this week, so I'm just going to go ahead and stop here. You do, however, need to know the vocabulary words sonic, supersonic speed, and sonic boom. Those will be on the quiz, as will the other vocabulary words that you were given last week. So I hope that this video was helpful. I'm going to go ahead and do experiment 14.1 on a separate video, as well as send you the video link to the YouTube video somebody else did that demonstrated the difference between a transverse wave and a longitudinal wave. And so I think that we are done. Yep, I think we're done for today. So good luck on your quiz, and I hope to see you all soon.